All right, so today we're going to continue looking at the periodic table. In particular, though, we're going to start looking at the periodic table for what it is, a model. Throughout the past few years in science, you guys have probably learned about quite a few different models, including this year where we spent a lot of time looking at the various different models of the atom. So if we haven't talked about it yet, that's what I want to talk about. What is a model? In short, a model is the representation of an idea, event, or process. And as with everything in science, it is supported by observations, data, and evidence. Okay, so these models aren't just things that are plucked out of thin air, unless you're talking about the Democritus model of the atom, which was more philosophy than science. But that's beside the point. So these models can be quite a few different things. They can be mathematical equations, like the equation that tells us the way that gravity works. It could be a graph, a picture, 3D sculpture, computer simulation, on and on and on and on and on. The important thing about a model is the way that they are used and what they're used for. Models are used to identify, express, and help us understand various ideas, as I said earlier. And the why of it is, well, why are they used? Things like cells, atoms, some long processes, especially that we see in ecology and stuff like that, they represent things that are difficult to examine, whether because they're big, they're small, it's a long amount of time, it's a short amount of time. It's a way for us to represent ideas that normally would be difficult for us to examine. So let's look at the periodic table as a model. First, we already know the periodic table of elements. It displays all the known elements that we are aware of, including ones that we as humans synthesized in a lab, things that don't naturally occur. In addition, we convey and we use them to represent various vital pieces of information. This could be anything from something as simple as the average atomic mass to using different colors, different numbers to show the state of matter, families, groups, which we'll talk about here in a minute. Are they metals or non-metals? And I've even seen some that go as far to show the atomic orientation, where they show a rough shape of those subshells that we learned about last unit. So they can be either very simple or very complicated. The thing about the periodic table, though, is that it is very uniquely shaped, and this is on purpose. As scientists, there's very little that is done on accident, and something that is repeated is definitely not done on accident. This shape is based on a variety of patterns and other similarities that exist among the elements, because the whole point of the periodic table is to put things in order. And we've already learned about some of these things. Some of the shape, or some of the locations, I should say, comes from their classification as a metal, non-metal, or metalloid. Some of the shape of the periodic table comes from the SP, D, and F electron configuration blocks that you learned about last unit. And there's going to be other patterns that we learn about here during this unit. So, the one thing that I will mention before we get into it is the main reason for the structure comes from the common electron configurations of the elements, which we will look at a little bit more in depth later this week. So there are two parts of the periodic table that I want to take time to talk through. First is what is called a period. Now, I've already talked about what periods are. But, as a reminder, periods are what I have labeled there in blue. These are the horizontal rows on the periodic table. Okay, these horizontal rows are called a period, starting with period 1, which is only hydrogen and helium. Then 2, which starts with lithium, 3, 4, 5, 6, all the way down to 7, which is francium, radon, so on and so on and so on. As we move left to right, atoms are gaining more and more protons and electrons. They are going up in atomic number. So left to right, they're gaining protons. Going top to bottom, the atoms are gaining energy levels. They're gaining shells. So, for the electrons that, let's say, helium has, it only needs 1 energy level. Whereas if we go all the way down to radon in row 6, it needs 6 energy levels. So, like an onion, there are these layers and layers and layers and layers. And as I talked about before, is what this term periodic means. Period or periodic is simply referring to the fact that something is predictable and repeating. There is a predictable and repeating pattern that we can follow. And in this case, that pattern has to do with the properties and characteristics of these elements. As I go left to right, as I add to the atomic number, there are predictable patterns that we can see arise. So, if I'm starting at the top, going from row 1 down to row 7, what would you predict would happen to the size of the atom as you go from row 1 to row 6? Okay, so that's periods. Moving on into groups and families. Now, this is where we're going to spend quite a bit more time. The periodic table is shaped. Its main shape is based on these repeating characteristics, as I said on the last slide. Much like Mendeleev kind of decided when he was putting together his periodic table, the groupings that we make are based on similar characteristics. So, vertically, in a given column, so column up and down, elements with similar characteristics are in the same column. And we call these either a group or a family. I personally tend to refer to them as groups. So, some of these families, I know I just said I refer to them as groups, but families. Some of these families have dedicated names, as they tend to appear much more frequently or are more important in other ways in chemistry. So, there's probably about 5 or 6 distinct groups that we're going to talk about. Not every single element is going to fall into one of these groups, but there are enough that they warrant us talking about them. So, using our trusty, handy-dandy periodic table, we're going to go from left to right. First is our alkali metals, and we already took some time, and these are the ones that were very explosive, we'll say, that I used at the beginning. I didn't talk about what it meant when I called them alkali metals, but this was the sodium and the potassium that I added to the water, and it exploded. So, alkali metals, such as lithium, sodium, and potassium, these are our elements that are in group 1, the very first column of the periodic table. They are very, very sharp, or not sharp, soft. You saw I was able to cut them with just a scoop tool. On the inside, they are very shiny, but they oxidize quickly. But their most distinctive property is the fact that they are very highly reactive. They react very violently with water. The next group of elements that we're going to look at is the other 2 elements that I experimented with, the alkaline earth metals, which is the next column over. These are the elements of group 2. So, the alkaline earth metals, like the alkali metals, they are soft. They are not nearly as soft as the alkali metals, but the alkaline earth metals, they are softer. They have some shine to them, not as much as the alkali metals, but there is some shine to them. And they react with water. As you guys saw with the calcium reacted very, very quickly. And while you didn't see the magnesium fully react, rest assured by the end of the day, it did. It just took much, much longer. The next set, and I'm kind of lumping all of these in together. These are what we call the transition metals. These are the elements that are in groups 3 through 12. And they are what I have highlighted in red. These elements, they have a relatively wide variety of characteristics. But some of the common things that they have with each other is they all conduct electricity. They are all relatively high density. And amongst other things, they will a lot of times be magnetic as well. And this is going to be the stuff like titanium, copper, silver, gold, platinum, tungsten, mercury. These are all transition metals. And we'll talk about this particular group a little bit more in depth, probably when we get back from break. The next group, and these ones tend to be the oddballs, the inner transition metals. These we refer to with two names, the lanthanides and the actinides. So our inner transition metals are these two rows that we have at the bottom. Lanthanides are the row that is on top, actinides are the row that's on bottom. So, unlike everything else, if you notice, I didn't assign a group number to these elements, because these actually don't have a group other than being actinides and lanthanides. These tend to have more in common with the other elements in their row than they do with the element that is above or below them. And they tend to just have more in common with each other. That's why they're kind of set to the side. Even though they do fit in our periodic table, these ones we tend to pull out and set to the side because they tend to have their own properties. One of the main things about them, though, is many of them are radioactive. So now, the next important set is what we call the halogens. Halogens is column 17. Group number 17, so the second from the end. These are mostly nonmetals, and these are highly reactive. And these are going to be things like chlorine, bromine, iodine, fluorine. Other than that, I'm not really going to go into too much. Aside from them being nonmetals, they don't have a lot of common properties with one another. Their properties tend to be more related in terms of chemistry. That high reactivity is very important when it comes to these halogens. And the last column I want to talk about is the noble gases, column number 18. Column number 18 is special because noble gases, these are non-reactive because they are what we call chemically stable. And we will talk about this property a little bit more in detail later. There's a certain rule that's going to come up that is very important, and it relies heavily on noble gases. But noble gases, they end every period. That's why that noble gas configuration, that's why we use it, is because we can say the end of such and such period is this noble gas, and use that as our shorthand to continue. The main thing to know, though, is these elements in this column, those noble gases, for the most part, are non-reactive. They are chemically stable. They do not like to react with other things. Lastly, because I am going to use this term, I want to make sure I mention it now. First of all, if you notice, there's still that big white gap in the middle of the periodic table. That is where our metalloids and and I've seen these referred to in different ways, weak metals or post-transition metals or light reactive non-metals. They have several different names. They don't really fit into a group. Anything that doesn't have a dedicated group name, we just call it whichever is the first element in the column, family. So, for instance, the carbon family is column number 14. Carbon, silicone, etc., etc., etc. But what I want to make mention of is this special grouping of elements. Groups 1, 2, and then 13 through 18. So everything except for the transition metals, everything except the transition and intertransition, are what we call the main group elements. These are the elements that are part of the S block and the P block, and they make up the bulk of the periodic table. And the reason that these have a distinction is that these are the ones that we will tend to see more frequently in chemical compounds. So, before I let you guys go, I have one more question. Based on what we know and what we just learned about the periodic table, and what you should have seen when you watched the alkali metal reaction video, the one that I posted the day that I did that reaction, what could you predict about the reactions of strontium and barium when mixed with water based on the reaction of calcium and water? So mind you, the reaction that you saw with calcium and water, what would you predict about the two elements below it? How do you predict strontium would react with water? And how do you predict barium would react with water? Based off of what you've already seen in terms of calcium and magnesium reacting with water. So, once you guys are all set with that, until next time, I'll see you.